previously we discussed that power is how fast the work is done, or since work creates energy, how fast the energy is being used. Symbol for power is P, and the unit is still watts. However, when we talk about electricity, we're usually not talking about work or energy. Instead, we're talking about things like current, voltage, and resistance. So we want to write down our equation in terms of voltage, current, or resistance. Now, power is energy over time. And in the terms of an electric circuit, it's more specifically how much the potential energy has changed because that particle, that electron more specifically, has moved within the electric field of the wire. So because that electron moves within the electric field, its potential energy changes, and how fast that changes per unit time is the power. We had said earlier that the change in potential energy is the opposite of the charge times the electric field times the displacement. And we're still dividing this now by time. Let's rearrange this equation and write it as the charge over the time, all times the opposite of the electric field times the displacement. We see that the first part of this equation is the current, charge divided by time, how fast the charge is moving. And the second part of the equation is the voltage. Now, we usually write it as delta V when we're talking about electrostatics, but in the case of circuits, a lot of times we drop that delta and we just write it as V. So power is current times voltage. Now, if we look at Ohm's law says V equals I times R. So let's replace this V with I times R, and we get a second equation of power is current squared times resistance. So if we're given current and voltage, we use the first equation. If we're given current and resistance, we can use the second equation. What if we're given voltage and resistance? Well, how do we solve for power then without going through any intermediate steps? Well, if we rearrange Ohm's law to say current is voltage divided by resistance, we can now go to this first equation and replace current with voltage divided by resistance. And that's still times the voltage. And so our third equation is that power is voltage squared over resistance. So again, depending on what we're given, if we're given current and voltage, we use the first equation. If we're given current and resistance, we use the second equation. And if we're given voltage and resistance, we use the third equation. So power is still, again, how fast the energy is being used. Symbols P, units watts. Depending on what we are given, we would use one of these three equations. Now, what is this representing? If we look at an analogy or an example, I should say, of a light bulb, let's say you have a 60-watt light bulb and you have a 100-watt light bulb. Well, which light bulb burns brighter? Well, if power is how fast the energy is being used, the 100-watt light bulb uses more energy every second. And so the 100-watt light bulb, since it uses more energy every second, will burn brighter. Unfortunately, that will make it also cost more because we're using more energy. So what a lot of times we do is we are going to use energy efficient light bulbs, those kind of swirled light bulbs, the incandescent light bulbs. The fluorescent light bulbs. The incandescent would be like a 60 and 100. The fluorescent light bulbs are ones that swirl, and those might only be 16 watts. So they'll cost you about a quarter of the price of what the 100-watt light bulb will cost you. So power, how fast the energy is being used, depending on what we are given about the circuit, we would use one of three equations to solve, measured in watts.